We'll be talking about the single facility Minisum location problem. This is a foundational problem from which we'll build out a lot of the location theory as we get into a variety of other extensions. This basic problem itself, if you remember from the previous lecture where we talked about the different types of location problems, this is an example of a cooperative location problem, and it is an example of a linear objective function. In the taxonomy, you had nonlinear, which is essentially all of the other types of objective functions, and the Minisum location problem is the single linear objective function problem that we'll be solving. Being linear makes it relatively easy to solve, and also it corresponds to a situation that in practice is actually appropriate in cases where, for example, you're paying a truck driver by the mile, which is true for most cases. First concept talked about in this lecture is the difference between monetary versus physical weights. And in general, when somebody in logistics talks about the weight of something being transported, by default they typically refer to the monetary weight, not the physical weight. And you'll see why that differs a lot. Even if the physical weight doesn't change, you can have differences in the monetary weight for a situation. This figure here shows the basic network structure. This is probably the most extensive you would think of. Here we have a single manufacturing plant, and it produces a single product, A. We'll call it product A. And A is composed of two major components, B and C. They're both produced at two other facilities, presumably at a different location. These would be the tier 1 suppliers. Each unit of B is composed of a unit of D and E, and likewise for C being composed of F and G. This side of the network is called the assembly network, and then from the plant all the way to the customers is called the distribution network. What changes is that the plant itself produces units of A, and then A doesn't change from the plant all the way to the customers. What does change is how large the loads are that move from one location to another. So this is meant to indicate that 2A's is meant to indicate that you might have a tractor trailer transporting product from the plant to the distribution centers, and then from the distribution centers to the customers, and the customers might be, for example, a small convenience store. You might have a small delivery van that transports smaller quantities to the individual customers. On the upstream side, so this is starting from the raw material all the way to the market, is called the downstream direction in the supply chain, and then from the market back to the resource is called the upstream direction. That same idea of relative transport size is carried over here. Here, the 4 here is meant to indicate you might be able to use something like rail transport, or these could even be ocean transport. You're basically you're able to ship large quantities of the product through the assembly network reaching the plant. This figure here has a lot of information in it. It basically shows a basic production system. You have a supplier, a customer, and the basic laws of physics apply here. So unless we're producing something nuclear where we would have a change in mass, the basic relationship that everything that goes in has to come out of the production system holds true here. So here we have 4 tons of raw material that go into the production system, but we're also adding to it 1 ton of a ubiquitous input. Ubiquitous input means that it's available at any location, so we don't need to include the transport of that input to the plant because you can get it anywhere. So that input would be something like water, assuming that wherever we would locate the plant, we can get water. So we don't need to transport it. So these are shown as being vertical. So we have a 1 ton of ubiquitous input, 4 of raw material. So we have a total of 5 tons being produced. But then to the customer, we're only shipping out 3 tons of finished goods. That additional 2 tons is scrap. And the assumption is to be scrap, by definition, it has to be disposed of locally. Say it's a hazardous waste and we would need to transport it to a disposal facility, then that would actually be considered a second finished good that is produced by the production system. I guess we could call it a finished bad instead of a finished good, but we'd have to take in the transport cost of the scrap into account. So without qualification, scrap means that we don't have to worry about transporting it. We can just dump it in a pit somewhere outside a facility, for example, but it can be disposed of locally. More typically, a municipal city or something would have the means to dispose of hazardous waste locally without having to transport. Below this shows a corresponding definition, and this is a term that we don't necessarily need to use a lot, but you'll hear it a lot, especially if you look at the business side of logistics. It's a term abbreviated FOB, and that stands for free on board. And it just refers to who owns the product when it's both inbound to the facility and when it's outbound from the facility. So, for example, on the inbound side, if a seller basically sells the product to the buyer, which is the production system, if they actually buy it at the supplier's loading dock and they own it, then it's called free on board origin. And then presumably then it's transported to the production system. In contrast, if the seller remains the owner of it all the way until it reaches the loading dock of the buyer, and only then does the title transfer, then that's referred to as free on board destination. The reason the title transfer is important is that, imagine halfway along the trip, the truck gets into an accident. Everything on board is destroyed, goes up in flames. Who's responsible for the loss? Well, in the case of free on board origin, at this point, the buyer would be out of luck in terms of, they've already paid for the product, so they have no recourse with the seller. Whereas if it's the seller's product all the way till it reaches the buyer, now the seller is on the hook for, making up the lost product, and the buyer then would not be affected. And then we have a symmetric thing that happens on the outbound side. In general, though, free on board typically, it impacts in terms of if you're taking more risk, you're probably going to want to sell the product a little higher on the free on board destination to cover your additional risk. Whereas free on board origin, you would tend to want to get the product for a little bit less because you're taking on the risk. So it kind of nets out in terms of what you pay for the product. From our point of view, in terms of the location of the facility and the transport cost, everything essentially nets out. So the location decision itself should be relatively unaffected by who actually is paying or taking title to the product. It's really more of a business issue than it is a logistics engineering issue. But it's important to be aware of this. This is the basic formula, this equation 1. This is the one that we'll be deriving a lot of results from throughout the semester for not just location, but when we get into transportation and into other areas. And it really does call out the difference between a monetary weight and a physical weight. So in this equation, W sub I is the monetary weight. So those are the weights that we talked about in the previous lecture. In those cases, the weight corresponded to the number of trips per day. But in this case, more generically, we're going to think of monetary weights as typically being provided in units of dollars per mile. And then that can be multiplied times the distance, so the miles cancel, and we end up with a total cost in dollars. This is an example of how the units need to balance out. So you can tell, what units the different variables need to be in, because we want everything to net out by having a total cost in dollars. Here's a more fine resolution of what actually does the monetary weight, what is it actually composed of? Well, it can be conveniently broken into two components. The first is the physical weight, which is in tons, and then the second is what's called the transport rate. And the transport rate is given in units of dollars per ton mile. And then multiplying times tons, the tons cancel out, so we're essentially then left with a monetary weight. So the physical weight times the transport rate gives you the monetary weight. So the monetary weight is really just a shortcut for not having to talk about both of these separately. In terms of terminology, an activity is called weight gaining or weight losing in terms of its monetary weight and not the physical weight. The next section of the lecture talks about procurement and distribution. And the idea of this section is to take what would otherwise seem like an abstract location problem and actually ground it in an actual, production situation. So, this is a simple problem, but it actually has really all the elements of an actual proper location analysis for a company. So we start with two different products, A and B. In the case of product A, Asheville is the supplier of the raw material. Customer is in Durham. We're going to produce product A. In this case, we produce 2 tons in, 1 out, so we have 1 ton of scrap. Product B is the opposite. Here we have 2 tons of the ubiquitous input that's added to the 1 ton of input, and we end up with then 3 tons of finished goods. So we have 2 different products. First question is, where should these 2 be located? Well, assuming the transport rate is the same for both of these, then the one that is losing weight, the product A should be located at Asheville. Product B, since it's gaining weight, should be in Winston-Salem. So that's, you can look at the problem like this and immediately know where should the products A and B be actually produced. So to add more detail to this example, this is I-40. These are the mile markers. So 50 means that Asheville is about 50 miles from the Tennessee border. Raleigh is at mile marker 295, and then I-40 ends at mile marker 420 in Wilmington. So with that as our one-dimensional location problem, and we want to be able to solve this easily by hand as a one-dimensional location problem. Again, remembering from the previous lecture where it was convenient, we don't need to get into the mechanics of using some computational method to find longitude and latitude. We'll be dealing with that later, but this is really just to focus on how do we actually get the monetary weights that we're interested in for this problem. So for example 1, we're going to start with the bill of material, similar to the example we just talked about. Here we have Asheville and Durham. And in terms of output, here we've normalized everything. So we have 1 ton of output. So to get 1 ton of output, we need to provide 2 tons of raw material. And we're ignoring the ubiquitous inputs and the scrap. So we don't need to specify it. But, this would imply that there's 1 ton of scrap. And here this would imply that there's a 1/2 ton of ubiquitous input to get this. So with this specified for these 2 systems, we can start with the input side, and basically in order to, and then this is actually specified for the problem. Where you get this is basically what is the recipe. The recipe is to produce 1 ton of finished product. We need to put in 2 tons of the raw material from Asheville, and then a 1/2 ton of the raw material from Durham. We put those 2 together. So we put together 2.5 tons to get 1 ton out. So again, that implies 1.5 tons of scrap that's produced at the production system to get 1 ton output. And then this is the same production system carried over down here. And here we're now looking at the distribution side. And the distribution side, what we're specifying here is what is the demand for these 3 customers. The customer in Statesville requires 10 tons per year, 20 and 30 tons. So in terms of solving a problem like this, we can actually formulate it as a proper location problem, and we could start off, and here I'm going to look into the code block itself. Line 1, we specify the tons per year. So these are the demands of the 3 customers. The output, R is the transport rate. So the output transport rate is $1 per ton mile. And then we can then immediately calculate the monetary weight by just multiplying the demand rate times the transport. So we end up with dollars per mile. And then to get the input side, we have to specify the bill of material ratios. So the 2 and the 0.5 correspond to these arcs right here, telling us essentially what is the recipe to get 1 ton out. So you can think of BOM as being the recipe to get 1 ton of product. How many tons of each of the 2 inputs do we need? Then to figure out what is the amount of input, because the way the problem is specified, we don't know how much actual tons need to come from Asheville to the production facility, and we only know that if we add up what the outbound demand is for the product. So we're adding up all of the outbound demand and then multiplying times each of these bill of material ratios, and then that gives us the amount of tons we need from Asheville, which is 120, and then 30 tons from the Durham supplier. And then we can multiply that times the transport rate. And in this case, the transport rate is actually 33 cents per mile, or 1/3 of a dollar. And that then gives us the monetary weight. So the monetary weight is 40 and 10 for Asheville and Durham, respectively. So we have these 2 monetary weights. We also have the customers' monetary weights, 10, 20, and 30. So with the monetary weights, we're able to actually now solve the location problem. And here shows code that solves the problem, but we can also do it by hand just as easily. So what I've done here is I've put the corresponding monetary weights below the coordinates for each of these. These are the different cities, and then these are the 2 suppliers and the 3 customers. And the important thing is to get the ordering right from left to right. So as long as you place the monetary weights in the correct order, then your location problem will work out correctly. And then the procedure then is to look at where the cumulative weight first equals or exceeds half of the total weight. Here the half of the total weight is 55, so we're looking for the location where we first cross that threshold. Starting from the west in Asheville, we cross it at Winston-Salem. And then if we had started in Wilmington, we first crossed the ratio again at Winston-Salem. And again, that's usually always going to be the case. If you remember from the lecture, the actual total cost curve is a piecewise linear curve that has a single point at its minimum. So the plant then should be located in Winston-Salem. Here's a related question. Is the plant weight gaining or weight losing? And here we're able to say that in the case of the actual physical weight, it is a weight losing. So it's losing physical weight. More physical weight goes in to produce a ton of output than comes out. But when we look at the monetary weight, it's actually a weight gaining activity. So in general, we would say this is a weight gaining activity because the monetary weight is higher on the output side than it is on the input side. And the reason for that goes back to up here where we have only 1/3 of a dollar for the inbound transport rate versus $1. And the reason for that difference is that here you might be shipping smaller quantities each time or using a smaller vehicle. Here the inbound side could be on large tractor trailers, which are going to operate much cheaper on a dollar per ton mile basis, while these are smaller delivery vans. So the difference in transport rate is really what's driving the weight losing on the outbound side. So this whole concept, if you keep this in mind as we go forward in other lectures, this will get you a long way down the road in terms of being able to have an intuition as to where would you expect the best location to be without having to really get too much into the details of how to actually solve a particular problem. The next part talks about single facility Minisum. And first it talks about the Fermat problem. This is a case where you have no weights. These are just equal points. And the important thing to take away out of this figure is that you can predict what the optimal location would be, knowing that the optimal point is going to be characterized, and it works only for 3 points, but the angles are 120. And this corresponds to a single minimum energy state, and it's called a Steiner point. So again, this is something, looking at a figure, you can kind of predict, well, I think the optimal location, assuming these all have equal weights, would be at a point about here. Here's another figure. It's called the Varagon frame. If you needed to solve a two-dimensional, like Euclidean distance problem, prior to the availability of computers, this was actually a hard problem to solve. So one of the ways people solve that is, again, locating a facility. If you're building a multi-million-dollar facility, it's worth taking the effort to get a proper optimal location. So what they would actually do is take a piece of plywood, drill holes corresponding to the location of the existing facilities, and then they would attach weights corresponding to the monetary weights of each of the existing facilities, and then they would tie 3 strings together at a point and let it find out where it came to a rest, and that resting point corresponded to the optimal location. So this is exactly the same optimal location that we're finding by using a computer and Nelder-Mead's procedure, for example. Here's a model format specification of our single facility Minisum problem. Here's an implementation. We're going to be using the optimize function. It's part of the Optim framework. So all we're doing here is basically picking a starting point, and we're going to use the centroid as our starting point. And then from that starting point, this function is using the Nelder-Mead procedure, and it's going to return the optimal location. Example 2 shows that for the Fermat problem, instead of having to just visually look at where the optimal is, we can use our same Minisum function that we've defined, solve it, and get the same optimal location as shown for the point in figure 8. Here's an example conceptually of what the total cost surface looks like. On the left side are contour plots, and these are the 3 existing facilities. The optimal location corresponds, again, this is the Fermat problem, corresponds to this low point right here. This is in 3 dimensions as a surface. Again, you can imagine, and the reason this figure is important is that what it really shows, probably the right side one is more useful, is that because it's a convex function, when we pick a starting point, the x0 starting point, it really doesn't matter what starting point we pick. Imagine like a marble. Wherever you start the marble, it's going to end up at the bottom of this basin. So starting point for a convex function really doesn't really matter. It's a convex bowl. You'll end up at the minimum no matter where you start. The next figure shows the operation of the Nelder-Mead procedure, and each of these points right here represents one evaluation of the total cost function. So you can see here physically exactly how the Nelder-Mead procedure actually finds the point. This is the starting point, and then it probes around and realizes it's getting a big decrease by going in this direction. So it keeps going in this direction because it's seen that the cost is decreasing. And then by the time it gets here, it realizes that, wait a second, in terms of the convex bowl, the costs are starting to go up. So here it effectively turns around and then heads back here. Here it actually overshoots a little bit what the optimal is. And then eventually the Nelder-Mead procedure narrows in on what is the optimal point. And once the decrease in total cost falls below some threshold, then it stops and says that's the local optimal solution. It's maybe not the global one. We'll see examples in other lectures where we have situations where each starting point may give a different final resting point. But in the case of having a convex problem, it doesn't matter where we start, we'll always end up at this optimal point. And then the rest of the lecture talks about other types of location objectives. These are some of the same problems that we saw in the previous lecture graphically, and this shows how we can use the same construct to actually solve these problems. One important point here is that for the maxi-min problem, we're trying to maximize the minimum distance. This problem only makes sense if we actually put a bound on the region. Otherwise, you just go off to infinity, go as far away as you can. So in this case, the optimal point here found is the one that is as far as possible away from these three existing facilities. Another name for the maxi-min problem is called the obnoxious facility. So if you have something like a garbage dump, you'd want to put it as far away from all the cities. And the natural bounding box would be like a county boundary, Wake County. What's the furthest point in Wake County away from any of the cities or towns in Wake County? And that would probably be a good point to put a waste facility. Section 5 introduces logjam. Logjam, we'll be seeing it throughout the semester. It basically provides capabilities to make it easier to solve location problems. Section 6 talks about what one of the things that logjam does. It provides basically a very simple and convenient way of calculating the different types of distances that we'll be using. The three most common ones, one corresponds to rectilinear distance, and the reason for the one is it's the parameter p in equation 2. So when p is equal 1, then you get equation 3. When p is equal to 2, you get equation 4. And then if p goes to infinity, you end up with equation 5. There is basically the difference between the actual road distance versus the great circle distance. And it turns out that for a lot of problems, it's very convenient to be able to use just the great circle distance as opposed to actually having to figure out the actual road path. If we have hundreds of points or something, it would be, really time consuming. Whereas if we calculate the great circle distance, we can just use a single formula that immediately calculates our answer in terms of great circle distance very quickly. So there's a big convenience associated with using great circle distances. But the problem is that in some situations we have problems where we can't really just look at the miles traveled in terms of great circle. We want to be able to at least estimate what would be the actual road miles. And typically that's done when we're trying to do some cost calculation. So if we have a transport rate that's in dollars per mile, it would be incorrect if we applied it to the great circle distance because it would underestimate the transport cost. So instead, we'd rather apply it to the actual road distance, but instead of calculating that actual road distance, we can do something called calculating an approximate circuity factor. So for this example, it's 1.14. So if we take the great circle distance of 121 multiplied times 1.14, we can then estimate what we would expect the actual road distance to be. And